Bene, good afternoon everyone. Welcome back. Are there any questions from yesterday? Any things you would like, any clarifications or any comments? Okay, so yesterday I really gave a kind of very quick survey of the fundamental concepts from a topological point of view, right? Basically the main concept is the omega limit of an orbit that contains somehow the information about the asymptotic behavior of the orbit from a topological point of view. And I gave some examples to always keep in mind that every time we look at these abstract definitions, it's good to have some concrete examples in mind. So today we're going to review some analogous concepts, but as I said from the beginning, using measures. So we have our map, we have, let's say, suppose some metric space, so that we have a measurable space here as well as a topological space, and we have our orbit. Right? And then, as I said, we will define this sequence of measures These are probability measures. So if we have a compact metric space, for example, and the sequence of the space of probability measures is compact in the Weak-Star topology, so we will also be, in some sense, looking at what limit points this sequence has, right? And what these limit points tell us about the orbit. In some ways, it's very analogous to the topological omega limit sets, but in some very important points, it is very different. And this is the purpose of today, is really to explore these similarities and these differences. So let's start with trivial examples, as usual, right? So what are the simplest example? If x0 is a fixed point, and what happens? It's always just the average of the Dirac delta is always an x0. So this is just, so mu n of x0 is just always identically delta of x0. And you know, the Weak-Star limit is also delta of x0, right? There's nothing really interesting is happening. Okay, now let's suppose we have a periodic orbit of period 2, for example. Let's just take the simplest, right? So it is also very simple, but it's not completely trivial, right? It's almost completely trivial. So here we have that mu0 of x0 is equal to delta of x0. So we have that mu1 of x0 is equal to 1/2 delta of x0 plus 1/2 delta of x1, right? This is the periodic orbit. This is kind of what you expect, right? But this is not stabilizing here, right? I mean, so mu2 of x0 is now equals 1/3 delta x0 plus 1/3 delta x1 plus 1/3 delta x0, because this is the second image, x2 is equal to x0. So this is equal to 2/3 x0 plus 1/3 x1, right? And then you can see already how it's progressing. So the next one is actually going to be half and half, right? So mu3 x0 is going to be again half and half, because it's going to be 1/4 twice on each one, right? So this is again half and half. Delta x0, delta x1. Mu4 is again going to be a little bit more concentrated on delta x0, but as you can see, this difference is decreasing. right? So it's getting closer and closer to half and half, right? So just like this. The last one, mu x0 is going to be, so we have 5, so it's going to be 3/5 delta x naught plus 2/5 delta x1. And anyway, we can see that in this case we're going to have mu n of x0 is converging to half-half. Okay, although I just want to emphasize that it's not as trivial as this, because it actually, infinitely many times it's not equal to this, but it's just converging to that as well. Infinitely many times it is. And obviously that's going to be the same thing for any periodic orbit, right? So if you look at this sequence of orbits, this is obviously what you expect to happen, because in the end, the measure that describes asymptotically this periodic orbit is just a measure that is uniformly distributed along the periodic orbit. Right? So this is x2, this is x period 3, then you have 1/3 of the measure on each one. So this is how you describe the periodic orbit. So what if the orbit, if the measure is not, if the orbit is not periodic? Let's look at the example where we converge to a periodic point. Again, the simplest example, right? So suppose xn converges to some fixed point p. So we have, here we have some point p, and we have x2, x3, x4, and somehow the sequence of points is converging. Okay. Then I will leave it as an exercise, but you can believe that this converges. Then mu n of x0, which is 1/n of this, converges to the Dirac delta P. If f is continuous, I guess we should use the fact that f is continuous. Or maybe not. Maybe we don't even need to use it. Just the fact that this converges to P. So this is just the definition of the weak star topology. If you apply this definition, okay, it's not completely trivial exercise, but I will leave it for you to do. Intuitively, you can see this, right? If you look at the measure of small neighborhoods of P, you can see that the measure converges to 1, clearly, right? Because if n is very large, this measure is uniformly distributed on all the points. The proportion of points inside the neighborhood as compared to the total proportion of points tends to 1, of course, right? So the measure of any neighborhood tends to 1, so the measure has to be concentrated in a neighborhood, smaller and smaller neighborhoods of the point P, so it converges to the point P. Okay, these are the simple cases, the obvious cases, let's say, or the expected cases. Now let's look at some more interesting cases where let's look, of course, at our favorite map, f of x equals 10x mod 1. So we know that we have lots of periodic points, right, for which we know that if we choose a periodic point, we're going to get that situation. We know that if we have a pre-periodic point, also it's in the end is going to converge to the periodic orbit, right? It's going to be a similar situation to this. If you have a pre-periodic point, you go around a little bit, but after some time, you start rotating on the periodic orbit, and you end up with the periodic point. So that's easy. So now, how about we take a fixed point, let's say the fixed point again 1/3 equals 0.3. And I want you to give me a point which does not land on 3, but which for which the measures converge to the Dirac delta. Okay. Can we have a point for which this is true, but which does not fall onto the fixed point, which is not prefixed? Exactly, exactly. It's the same as yesterday, right? So what you want is you want it to spend, it's not really just about having a subsequence, right? But the amount of time that it spends near that point needs to tend to 1, right? Intuitively. Again, I don't want to do the calculations for this, but if you take a small neighborhood here, so you can take, for example, x0 equals 0.131, 331, 333, and so on. Okay, and you can see that the proportion of 3's becomes very large, right? So you have a lot of, you definitely, if you look at the first 1 million digits, you will see that the time that it spends in a very small neighborhood of this is converging towards 1, right, as n tends to infinity, because when you take very large n, you will have 99% of 3's with huge blocks of 3's, so you will spend most of your time inside here, okay? But this point is a repelling fixed point. It's not an attracting fixed point, right? So this orbit spends all of its time here asymptotically. The statistics of this point are that it spends asymptotically all its time in this neighborhood, even though the point itself is repelling, because it always escapes the neighborhood as well. This is an important example to digest in some sense, because it is the first moment in which the measure theoretic and the topological start to diverge a little bit. Okay, not in a very significant way, because it's still topologically this is a limit point. This will also have some other limit points, but a more interesting case is, can we find an example where the orbit is dense, but still the measures converge to 1/3, to this point here. So we want this to happen. We also want omega d is equal to all of this one. Can we do that?
As yesterday, but we add a lot of free.
Exactly. It's the same way, right? That's why I spent some time yesterday, thinking about that. So all you need to do is the same example as before, but you start with a orbit which has a dense, which has all the finite blocks, and then, as I emphasized yesterday, you can put whatever you want in between the finite blocks, and we start putting huge numbers of 3's in there, right? Lots. You need to have big, because you need basically to make sure that if you look at the first 1,000 itlets, then 90% of the time you have 3's, and then if you look 1 million itlets, it needs to increase to 95%, and so on, right? So you need to make sure that the proportion of 3's is converging to 1, basically. But it's very easy to do. So there's lots of points. There will be infinitely many points, in fact, that have that property. Okay, now let's take this one step further. What about an example where the sequence does not converge? So what about an example here with mu n of x0 where this sequence does not converge? So it has 2 limit points, for example, or multiple limit points, right? So does not converge if it has more than 1 limit point. we do that? Easy, right? By now we're professionals at this. What does it mean? This is going to be a very subtle point as to what it means to have several endpoints.
Something like before, with a lot of 3, then a lot of 4, and maybe then 3 and 4.
So what do we mean by a lot? Yeah, so let's take 5 here just to simplify things. So how many a lot is a lot?
Enough to move the
The average.
average.
Exactly, right? So you need each time, you basically need to increase by an order of magnitude each time. You can't just put a certain number of 3s and then twice as many 5s and then twice as many 3s. You really need to dominate that, right? So you need to have 0.3 and then you have, say, 3 5s, okay? So this is now when you get to here, you've spent 75% of your time here, but then you want to put a lot of 3s, okay, so that by the time you've got here, these 5s become negligible, or at least become small, right? So you want a sequence which is an order of magnitude larger, and then you want lots of 5s by an order of magnitude more than everything that came before, so that those 5s dominate. And then what you're doing is you're spending your time, right? So you're you take your orbit, and then you're spending a lot of time near 1/3, right? And then you arrive here, and then suddenly you've got 1,000,000 5s here, so you're very close to 1/2, and you spend a lot of time near 1/2. And if you wait until the end, if you wait here, and you look at this sequence, mu n of x naught, up to this time here, you will see that most of your points are here, so you spend 90% of the probability measure is in a very small neighborhood of 5. Right? And then you put something of a higher order of magnitude here, and then you spend, after that, if you wait until you've done all that, then you say, oh, sorry, I made a mistake. I was spending actually 90% of my time here. And so on. So this for me is really the key example that motivates everything we're going to do in some sense, right? And I think it's really worth spending a bit of time. Sometimes, basically what we're going to be doing in the whole course is trying to show that this is a pathological situation that almost never happens, okay? But you know, if you don't realize that this is what you're fighting against, you lose a lot of the motivation for everything that we're doing, because what we're doing is really trying to show that usually the statistics are well behaved, right? So what does it mean here that the statistics are not well behaved? It means that the statistics, which means the proportion of time that you spend in different places, depends on the time scale. That's what we're saying, right? That depending on the time scale, if you look at a few hundred digits, then you see a certain behavior here. If you look at a few million digits, you see a different behavior, right? So this would be analogous. What would be the analogous? What would that mean if this is how when you flip a coin, right? What would you observe if you had this kind of situation when flipping a coin? So this would correspond, if you apply this kind of behavior to a coin, what it means is that the statistics, which means the average number of heads or tails, would depend on the time scale of the number of flips, right? So it would be like saying, okay, if we flip the coin a few hundred times, we get 90% heads. But if you flip it a few thousand times, we get 90% tails, and so on, right? So this is saying that the statistics depend on the scale. In this case, we're looking at the dynamical system in time, but the same concept you can apply to any statistics in space, right? So in science, I'm not a scientist, I'm a mathematician, but in science, I guess it's kind of almost an assumption that you can take samples and you can measure the statistics of a sample and you can extrapolate that statistics to the whole population or whatever, right? So you're always in science, I guess, in physics and biology, you are kind of assuming that you can go at different scales and you do not, and you see a similar statistics, at least if you take your samples correctly and so on, right? Whereas this is a nice example that shows that in very natural situations, you may not have that scale. You know, it emphasizes the fact that that is a non-trivial assumption, to me at least. Of course, in nature, usually you don't have things across too many scales, right? The physical world is kind of limited. In mathematics, we can talk about millions, billions, you know, we have arbitrarily large scales, so we can talk about it like that. But I think this is really important to keep this in mind. So the question is, how typical is this bad behavior? Right? The fact that these statistics does not converge. This is where I want to emphasize the difference between when we take the tautological omega limit and this measure theoretical limit points, right? So when you take the topological omega limits, it's natural to take all the limit points. You don't necessarily want the orbit to converge, right? The sequence of limit points, like if the orbit is dense here, that is meaningful to take the whole space is a set of limit points, okay? But in the case, there's a huge difference when we look at probabilities. We really want the sequence to converge, right? If it does not converge, it's a mess. This is exactly. If it does not converge, it means that on some time scales you see one statistics, on different time scales you have a different statistics. Okay? Of course, converging to a measure is still a measure distributed in space, so it's not converging to a point, right? It's converging to a measure that describes something in space. So it's not limiting the fact that we want that sequence to converge. Okay, so basically the spirit of what we're going to do in this course is to establish conditions under which this sequence converges. This is really the main topic of ergodic theory, essentially. Is, okay, when does that sequence converge? Because if that sequence converges, then you're really describing, so for example, one of the main theorems we're going to prove later in the course is theorem, and we state it here, is for 10x mod 1. Okay, so for this example, for Lebesgue, almost every x in S1, we have that mu n of x0 converges to Lebesgue. This is going to be one of the main theorems that we're going to prove in this course. Right? And this is a very remarkable theorem. First of all, it says that for Lebesgue almost every point it converges, okay, which is good. And then it says, what does it converge to? So the fact that it converges to Lebesgue is telling you that basically that if you take an interval here, A, it tells you that the orbit is uniformly distributed in the interval, right? Because it tells you that, so this sequence of measures that is uniformly distributed on the orbit converges to Lebesgue, which means that if you take very large n and you look at the proportion of points in the orbital line in A, this will converge to the measure of A. Right? So it means that all the points, almost every point, yeah, exactly. Yeah. And this has some very interesting applications, which I just mentioned. Now we're going to, when we prove this theorem, we'll look at them more in depth. But for example, it means it has some implications for the decimal expansions, right? Because if you take, for example, the interval between 0.3 and 0.4, right? Then it says that almost every point will spend 1/10 of the time in here, asymptotically, because the Lebesgue measure of this interval is 1/10, right? And when is what can you say about the decimal expansion of a point that falls in here? It means it has a 3, right? If you look at the decimal expansion of the point, I'm getting a little bit diverted here, but I think it's worth just making a very small diversion here. If you look at the decimal expansion, 0.1, 3, 7, 4, 8, 2, 3, right? So every time you see a 3, then it's going to fall inside this interval here, between 0.3 and 0.4. So the fact that we have this theorem here is saying really that we will look at it more precisely, but saying informally that the time it spends is converging to 1/10 here, which means that if you look at asymptotically, the number of 3's in the decimal expansion converges to 1/10 for almost every point. Right? Which is something you probably know already. This is sometimes called in probability theory the law of large numbers, basically this. And it's really a kind of dynamical proof like this. Any questions? Okay, so how do we, we formulate, I want to say a little bit how we're going to set up our questions, in some sense, in a systematic way. So we're going to always work, we're going to be particularly interested in cases where X is some kind of manifold, so that we have the Lebesgue measure. So in our, when we say that we want to show that this pathological behavior, that this lack of convergence is pathological, we need to have some kind of reference measure, okay? For simplicity, we're going to assume we have some Lebesgue measure, right? We have some compact manifold. In our case, usually it's just the circle or the unit interval. We have Lebesgue measure. And then if we have a mu is any probability measure on X, then we define here the base, and we use the same notation as in topological sense, but means something different, is the set of points x naught in X, such that mu n of x naught converges to mu. So to begin a systematic study, because here we just look at some examples, right? So to begin a systematic study, it's useful, instead of just taking every initial conditions and try to understand what's happening, we take a probability measure and we say, okay, are there any points whose Dirac averages converge to that probability measure? Right? So of course, in principle, this is empty in general, but we have seen some examples in which it's not empty. If you have a contraction map and everything converges to P, then you take the Dirac delta in P, and then the Dirac delta. So let me write an example. So if F is a contraction, okay, then D of delta of P is equal to the whole space, right? Because we have delta P here, all the points converge to P, and we just said at the beginning that if you have an orbit that converges to P, then the Dirac averages converge to the delta on that fixed point. Okay? In this theorem here, it also implies that here we have almost every point satisfies this. So in this case here we have the measure. So almost every point belongs to that basin, right? And indeed, what we're interested in. But if you have if you just look, for example, at not every point satisfies this, right? So if you look at the Dirac delta on one fixed point, there will be some initial conditions that have that property, but it will be a set of measures zero. So what we're interested in is we say that mu is a physical measure. If a Lebesgue measure of B mu is positive. So this means that all the points in the basin have the same statistics, right? When you take n very large, you look at the orbit, and the time distribution of the orbit is very close to the measure mu. So the measure mu is telling you where the orbit spends most of its time, right? If the measure mu is distributed in a certain way, it's telling you what happens when you have convergence. If this basin has positive Lebesgue measure, it means that you have a positive Lebesgue measure set of points that has the same statistics. Right? So that means that that statistics is significant for the system. We assume here that Lebesgue measure is your reference measure. So when we look at this dynamical system and say, okay, we would like to try to describe the dynamics of this dynamical system, it means not just that we know it has a repelling periodic point or some other periodic points. We need to describe something for a set of positive Lebesgue measure to be satisfied, if not a full Lebesgue measure. Right? So we're looking for the typical dynamics of orbits here. Okay? As you can see from the example of 10x mod 1, it's unrealistic to understand the dynamics of every single orbit, because we have all kinds of crazy behaviors you saw from this example. You can construct points whose omega limit is more or less whatever you want, whose Dirac averages converge to whatever you want, right? So really, the only hope we have is to be able to say, okay, almost every point does this, okay? So we're looking for physical measures. We're looking for a certain number of physical measures. So there is a conjecture, there is a big conjecture in the field that is still wide open, really. This was formulated by Pallis, mathematician in Brazil. This is back to the 1990s. And this conjecture is the following, is that for typical dynamical systems, systems have finite number 1 to say mu-L. Okay, and the basin and the union of the basins has full measure. So I'm not, a little bit beyond it, I'm not going to say what typical dynamical system is. Maybe we can talk about it towards the end of the course, because there's various ways of describing typical. You have some topologies on the space of dynamical system, or you have some, so you can talk about typical as a kind of a open and dense set, or you can talk about typical in a measure case, but there's various ways in which you can define typical. Okay, let's leave it on an intuitive level. But the philosophy of this is that when you have a finite number of physical measures whose basin has full measure, it means that you only have a finite number of possible statistical behaviors with full probability in the system. This is the philosophy of this. Right? So in some way it's trying to capture the idea that this is a regular, relatively regular behavior. Right? Even though the statistics might be very wild, right? For example, in this case, remember we talked yesterday about the fact that 10x mod 1 has this sensitive dependence on initial condition. If you take two nearby points, completely different things happen. But remarkably, even though you have that kind of unpredictability, as I mentioned yesterday, this is the statistical predictability that I was comparing to the average temperatures or the average flips of the coin. Right? So that is exactly the system in which you have short-term unpredictability, but long-term statistical averages. And what this is saying is that that is a typical behavior that you have this. This may be false, this conjecture. So far, there's been a lot of work, there's a lot of very high-level work going in this direction. I think the most important thing about this conjecture is that it has motivated a lot of very interesting research. So we now have a lot of work. My own field, in some sense, is really very much along this direction, you know. So a lot of work has gone where we have, say, made most progress is in defining which kind of systems have this property, which kind of systems have physical measures. But where it is completely wide open is to know whether these kind of systems are typical in any way. This we really do not know. Okay, so before we before we go on, let me say that there are examples which do not have physical measures. Can you think of an example that does not have a physical measure? Sorry? Exactly. When you're looking for a counterexample, always start with the event. Because, as we said before, every point is fixed, so the Dirac average of every point just converges to itself, like mu n of x0 is just equal to the Dirac of x0 for each point. So there's no measure that can have a positive base, positive measure base. There are also examples, but I'm not going to do them here also because I'm not an expert in these actually, and I've not really read the details of the construction. But there are some relatively simple examples that do not have physical measures because the average does not converge for Lebesgue almost every point. Right? So, like the example we did before, we constructed a point where the average does not converge. You can construct examples in which Lebesgue almost every point has this kind of behavior where the averages have multiple limit points. Okay, there's some very interesting examples. There's also examples where you have an infinite number of attracting periodic points. So every attracting periodic points has a little neighborhood that converges to that. So it will have positive Lebesgue measure, but it's a countable number of orbits and they have very, very small basins. So you have examples where you have an infinite number of physical measures. So when you say typical, it really means typical. You cannot show this for every system, right? So there are systems in which it's infinite, there are systems that have no full measure, but these are all exceptional examples in some sense. Okay. Any questions on this? Okay, so this was again really just an introduction and a motivation for the subject. So now we're going to start with the formal definitions that will allow us to build up a theory. What I'm going to do in the course is, as I said, I'm going to prove this theorem and a generalization of this theorem. So this theorem applies to 10x mod 1, but it actually applies to more general class of maps. So what I certainly would like to do is prove that theorem, and then maybe we will go a little bit beyond that. So the first concept that we need is the concept of invariant measures. We have metric space X, we have a map X, and we say definition. Mu is F invariant all measurable sets A. So mu is F invariant if for every set the measure of the pre-images is equal to the measure of the set. So we'll give several examples now in this case. First of all, let me say that the theorem that we're going to prove, I think, I don't know, maybe probably next week, is that we're going to show that F is continuous, then any limit point of the sequence mu and with 0 is invariant. So this means that if we're looking for these limit points, that it means that if F is continuous, then every physical measure must be invariant, by definition. Right? A physical measure is invariant if it has some sequence that converge to it. This is more generally saying that any limit point is necessarily invariant. So this is a kind of intrinsic properties of the limit points of the sequence. Right? So if we take a sequence, any limit point is necessarily invariant, it satisfies this definition. And then it will turn out that remarkably invariant measures themselves have a lot of dynamical consequences. So just knowing that a measure is invariant is going to imply quite a few things, quite remarkable things about the dynamics. So first let's give a bunch of examples here about invariant measures. Invariant measures. So we keep going through the same examples. So if P is a fixed point, if delta P is invariant. So P is a fixed point. So let's just check that together, right? Even though it's a very simple case. So we want to show the delta P of inverse image of A is equal to delta P of A. Is that true? So there's two cases for delta P of A, either 0 or 1, right? So we need to check that it's either 0 or 1 in this case. So suppose A does not contain the point P. What can we say about F minus 1 of A? It also cannot contain the point P, because if F minus 1 contains the point P, P is a fixed point, so it would be containing A as well. Right? So in this case it's easy. So if P does not belong to A, then P also does not belong to F minus 1 of A, and therefore they both have measure 0. Okay? And similarly, if P does belong to A, okay, then it's clear that P must also belong to F minus 1 of A. Right? Because P is a P-image of itself, so it also belongs to F minus 1 of A. So if P belongs to A, then P belongs to F minus 1 of A, and so they're both 1, so delta P is invariant. So for periodic points, I will leave it as an exercise. It's the same thing. So if you have a point, let me write it down. You can check it by very similar arguments. So if P0 Pk minus 1 is a periodic orbit, right? Then you have mu equals to 1 over k P0 plus 1 over k minus 1 is invariant. So again, this is what you expect. You just, because you go backwards, you go forwards, you can see if you take one point here, if you take any number of points. Here, this measure, of course, just counts the number of points, right? It's got equally distributed on these points, and you can easily check that this is invariant. Okay, what about the circle rotations? If you have here f of x equals x plus b mod 1. Remember the circle rotations that we looked at last time. X 0 b. What measures are invariant here? So first of all, when b is rational, remember what happened when b is rational?
It's periodic.
Every point is periodic. So you have these measures here on the periodic points. Okay. Yes, I'm also. Okay, there's a small. Maybe I will write it here. I think we can just. So we left m of equals the space of invariant measures, invariant probability measures. So invariant for F, right? And then it's quite easy to show the position again. This is one of the exercises, is that MF is convex in the sense that the linear combination of two invariant measures is also invariant. That you can just follows immediately from the definition, right? So if we have two fixed points, P1 and P2, and you take the measure, half on the third on P1 and 2/3 of P2, this is just invariant in exactly the same way because each one is invariant of its own. Like you don't need to have a probability measure here, right? So, sorry, maybe I should have had this. So if this is 2 P and Q, right? And you take the measure mu equals say 1/3 of P plus 2/3 of Q, then you do exactly the same calculation and you see that this is invariant also. So in fact, any convex combination, mu T plus 1 minus T Q will be invariant. And you can easily check from the definition just that this is true for any two invariant measures. Right? So if mu1 and mu2 are invariant measures, then you have that T mu1 plus 1 minus T mu2 at T is between 0 and 1. This is also in the space of invariant measures. So this means that for the circular rotation if B is irrational, you have the periodic points. You have all the convex combinations of these measures on the periodic points. What else do you have besides this that is invariant? There is one obvious measure that is invariant here. The Lebesgue measure is also invariant. Because it's just translation. Right? So if you take a set A, its pre-image is another set A that has the same length. So in the invertible case, we could have used just measure of f of A equals measure of A, but in the non-invertible case, these two are not the same. So let's look at our map 10x mod 1 again. So in this case, it's useful to look at it, to draw the graph of the map. And 0, 1, 0, 1. So 10x mod 1, as we said, has 10 branches here. Okay, 0.3 and so on. Okay, so let's take a set A. What does the pre-image of the set A look like? So you can see that 10x mod 1 is what we call a full branch map. This is the class of maps that we're going to study that I said we will look at a more general classes than just 10x mod 1. One of its key characteristics is that it has a partition here, and each element of the partition is mapped bijectively onto the whole interval or the whole circle. Right? That's what we mean by full branch. it has 10 branches. Each of these is a branch, and these are called branches because they're branches of pre-images, right? So each point in here has one pre-image inside this interval, because there's a point here that maps to this. It has another pre-image inside this interval. It has another pre-image inside this interval. Right? So each point here has exactly 10 pre-images, one inside each branch. This is the structure of full branch maps. It's the one crucial aspect of the structure. And in particular, A has this interval A, we have a pre-image here and a pre-image here. Okay, each one will be an interval. And what is the size of each of these intervals? Sorry? Yes, because the derivative is 10 here, right? So this one is stretched 10 times to map onto here. So this one is exactly 1/10 of this, and there's exactly 10 of them, right? So the measure, the Lebesgue measure of the pre-image of A is exactly equal to the measure of A. So here we have also that Lebesgue measure is invariant. For a very different reason than from the circle rotations, right? In a very different way, it's invariant. This also shows why the definition of invariant uses this backwards, right? Because if you look at this example, this makes sense, right? Because this is the natural way to define invariant. It wouldn't make sense to say that you want the image of every set to be the same as the measure of the set, because in this case, this maps onto A, but really there's lots of intervals that map to A, and you want the collection of those to amount to have the same measure of A. Like that. So that explains really why you want this definition to be in terms of the pre-images in the non-invertible case. Notice also that in this case, the Lebesgue measure coexists with lots of other invariant measures, right? Because here we have all those periodic points, all those fixed points as well. So we also have all the periodic points, the Dirac measures on the fixed points, all the convex combinations of those, and Lebesgue measure. So in general, you may have a system that has uncountably many. In fact, we shall construct later on in the course some other invariant measures which are not atomic. They're not Dirac deltas, but they're not Lebesgue measures. They're singular with respect to Lebesgue, but they're continuous measures. Some very interesting measures, invariant measures on subsets of this. Okay, and then the last example I want to give may be, no, I want to give two more examples. So why don't we take a little break now, take a 10-minute break, and then we'll continue with a couple more sophisticated examples. Sorry, I just